Okay, good afternoon, everyone. So today we are going to study about decision trees, and most of you who are doing DSA will be knowing about trees and how they work. And anyways, we'll learn about trees in shorts, right? In short, so a tree in biology or in real life, what is a tree? It has a root, it has branches, it has leaves, right? So basically in mathematics and computer science also, trees have a root, and from there are branches, and we get to leaves. So basically if I could show the structure of a tree, so there will be some nodes, and those nodes are connected. But how are they connected? So at the first, we'll be having a root node, and this root node will have, say, a number of branches, say 2, 3, 4, any number. One, it can be one, and then we'll have a new nodes, and then they will branch out, and that is how a tree is made. Just a second, I'll just set up. Right. Let me share my screen. Right. So this is where we have the node, the root. Right. This is just a tree for now, right? And then we are going to have, say, some branches, and then there will be some nodes. Then they will have their own branches. Some will have one, some will have two, some will have multiple. And let's say this doesn't have any branch, and then we'll have nodes. And finally, if say for example, this this didn't have any further any nodes. So this one is we call the leaf. This will also be called the leaf. Let's say this had some branches, so this will be called the leaves. And then this is a leaf, and this is the internal nodes of the tree, right? This is what a tree looks like, and we won't go into much details of how tree works. Basically, there can be some values. Say, for example, here we have, then we'll be having some values, say 3 by some relation. Let's say this side we have 3. Here we will have some value which is, let's say, greater than 2 square. So we will have some like 5. This will have some value, let's say, greater than 2 cubed. Let's say 9. Here some 20, and that's how we'll build a tree. Just a second. Very sorry. Yeah. So now we come to decision trees, and we'll use this structure to form models. So what is a decision tree? In decision tree, we'll be having a number of decisions that are taken at every node based on some feature, some parameter, and will proceed downwards, right, to the leaves. So let us say that, say for example, if it is going to be rainy or not, right? So is it going to be rainy or not? And then we have some features, say as example the humidity, then the temperature, maybe the pressure, and so on. And we need to predict if it's going to be rainy or not. Mind you that in the previous sessions we were doing on regression. This particular question is a classification, because the answer will be either true or else it will be false, right? So this will be a classification task. I'm saying this for the classification task because decision trees are, you can say, it is easier to explain a decision tree in terms of a classification task than a regression task. So that's why I've chosen this example. And in what we do in decision trees is that, let's say we take a node, right? Square, and let's say we take one of these features, right? Let's say humidity, and then we find, let's say, if it is less than 60 or whether it is greater than 90. We could also have, let's say, less than 50, then less than 75, then greater, and the rest, so some greater than 75, right? But the thing is that, yeah, so instead of doing this, we can actually go for a 2 and then a 2 division. So let's say first we divide on the basis of 50, and then in the here we divide on the basis of 50, and here we divide on the basis of 75, right? So we can do that as well. So when this will be greater than 50, let's say, and this is less than 50, so and then here we can divide, say, on the basis of less than or greater than 75, right? 75, this is greater than 75, this is less than 75. So for now I'm considering only three branch, only a binary tree. So this we have only 2 branches, or maybe 1 or 0 branches. So 0 branches means a leaf obviously. So tree with at max 2 branches, and if 3 branches are required, then we can divide the thing into 2, and then from there again 2 more branches, right? So let's say we did this kind of division, and then we are dividing, say, on the basis of temperature. Now here we are dividing, say, temperature. We know the temperature is only low or high, we don't know the exact value. So this goes as low, this goes as high, right? And then if this is 50 and low, then 50 and high, and again here we can have several pressure, right? So the basic thing that I want to tell you is that uh, it doesn't have to be that this row will have to have the same the same parameter. It can have different parameters in the same height, at the same height. 2 different parameters can be there, but basically whenever we'll go we'll go one depth at a time, right? So this is one depth, then when we are going here, then we'll have all of these will have some parameter or the other, right? Then we'll go to depth 2 here, and so on and so forth. Okay, so this is a very rudimentary rudimentary visualization of the decision tree. So basically in decision tree is a tree where at every node we are making certain decision based on certain parameter or features that are given to us, right? Yeah. So let us see an example before moving on to more theory, right? Let me just share my screen. Somehow this sharing is not working. I don't know why. Just a second. Okay, my Zoom portal is not visible. Why I don't. Shanaz, are you there?
Yes.
Could you just pause the share? Just pause pause the recording.
Just a second. Actually, you're the host.
Okay. No, I guess I need to exit because somehow. Okay. Okay. Let's see if I have got this. Okay. Okay. Is a collab visible?
Yes.
Okay. So let me give an example on a different data set. Let's say we go for the iris data set, and we have the decision tree. So we'll go for decision tree. Let us just connect it. Let's click on the tree. Yes. Okay. So we got the iris data set, right? And let us check the iris data set works. Oh, sorry. So you can follow me if you want to, because I'll be typing it out, so you'll have the time to type and check for yourself as well. So basically, the iris data set contains this, that there's this 4 types of attributes. Okay, so we have the sepal length, the sepal width, the petal length, and the petal width, right? And then with this kind of information, we want to predict if it's setosa, versicolor, or virginica. So there we have three three we have 4 features, and we have 3 kinds of output, right? So this will be 3 outputs. It says 0, 1, and 2. So let us have this data and features. So this will be the features, and then we can also have the target, right? For now, I'm not splitting it. You can always split it. The previous session I told you how to split, 10 test split from sklearn. You can use that. You can do it on your own, anyways you want it to. And so we can have decision tree equal to, and we can just use this and fit features comma target. Okay. So if we do that, we'll have something. It will just return this what it has been initialized with. So we'll have this criterion Gini. I'll come to this thing later. What is the Gini criteria? And all these are default values. We haven't set anything. We'll set and try how these things work out to be. So for now, let us say, for example, try out how much error we are having. Let's say, okay. So we can go for the MSE, right? Mean squared error. Oh, sorry. Error. And here we have the target, comma, LTT dot predict, right? And this will be features. Get error. Okay, so it seems that it has fit exactly to the data. So it has almost it's kind of marked up the data. Okay, let us then try with train test split, right? From sklearn dot model selection. We'll try the same thing. And test split, right? And we can have our X train, Y train, X test, Y test, equal to and test split. It will be the input. So we'll have arrays. Okay. And options. So the parameters will be arrays, which will be list and then chain size, test size. Okay, fine. Then we'll have features, target, set a test size equal to 0.2. We having the variables. Let us just check X train and Y train. Okay, so I did a mistake right there because X test will, yeah, I did a mistake. Let me just correct that. Now we have it. Yes. So can delete this. Okay. And let us train only on the X train and Y train. So, and then predict on target and on, let's say, X test. Oh, sorry, not on X test, Y test. And here we'll have X test and get the mean squared error. So this 0.66667. And okay, that is the model has classified very well. Okay, let us shuffle this then because it was not shuffled. So let's shuffle it. Okay, see, I could have done this before and shown you the thing, but I want to show you how to think and what to do and how to do this. So that is why I'm focusing on showing you how it is being done. 0.3. Let's see. Okay. That's nice. So it seems that the model has been predicting very well because it is a very small data. So that is why the prediction is very good. Okay, but moving on, what is important here is to learn it, is to understand the theory and how it is working. So first of all, let us visualize how the decision tree is working, right? So I'll import and a few libraries, and okay. So from IPython display, basically what happens is that in these kind of notebooks, which are called IPython notebooks, you see, this is IPyNB. So basically, the displays works different than you would work in normal in Python. So say for example, uh, what you would do is that you would go for import. Okay, if you don't know what is CV2, CV2 is for visualizing images. Right? If you want to work with images, then often you will come across using CV2. You can also use there's also PIL. That library is also there below. So there's something called cv2.imshow, and what it will do is that it creates a window. So if you do it there in your normal Python, say in a normal Python file, and you that run that file using your interpreter, then it will create a new window where it will show you the image. But what happens here is that this is running in a server. It's a different kind of thing. It is working in a server. We are just viewing the interface. So cv2.imshow doesn't work here. It will rather create an error in when it will work. And so similarly, for viewing images, often we use IPython library. So just in case, whenever next time you see this IPython, you know that this is particularly for IPython notebooks that you have, right? Okay. So let us visualize this model. And okay, we need another library. So sklearn import tree, right? So let us see what we have. Tree dot. Okay. You see, this is export graph is, we'll use this. Okay, we'll visualize the graph, and we have the decision tree, we have dt, we also have, let's say, the feature names. So we'll use the feature names equal to iris dot, let us see what are the feature names, right? And then we'll have the class names as well. So we'll have the class names as iris dot, let's see what are there. Okay, okay, target names, right? So we'll be having as img, or it can be say graph as well. Let's do graph img, it's not good variable. Okay, so now what we can do is, using pi dot plus, we can have the graph from dot data. Okay, so this is not graph, this is dot data. And next we are going to have sorry, dot data graph. Yes. So now I will just bring to the graph. Graph dot. We should be having something called create graph or create dot, right? No, sorry, create will use the image. So create JPG, we can create JPG, we can create PNG. Let's create a PNG. Let's see how it is working. Seems this function. Let us try another one. Let's say we create, it's a JPG. Okay. Okay, I understand what is happening. Let us use another. Oh, okay. Okay, okay, okay. I wasn't creating a function. It is why the problem was there. Right. Okay, now I understand. What was right, right. Sorry. Yeah. So as you can see, here we are dividing on the basis of petal length, first of all, and then we are dividing here on the basis of petal width. Again, here we have petal length, and then we are getting the various classes, right? So this class setosa. So if something like this comes out, then we'll have setosa with petal length greater than 2.45. If it is less than 2.45, then again we'll have, for petal width we'll have 1.65, and then so on and so forth, right? So basically, this helps us to visualize how the tree is functioning. And one of the major features of decision trees is that decision trees help a lot in understanding and in visualizing how it is working, right? So there's also another type of visualization that we can do. I'll not be writing the code for that, but I'll be showing you something. Let me just open that code, and it's called the division. Decision boundary. So what is the decision boundary? Let me show you, and you'll understand what is the decision boundary. Just a second. Sure. Right. Okay, let me just share my desktop. Okay. So basically, this is a decision boundary. Let us see here. Yeah. So as you can see, just forget about everything else. Just see this image, see this graph. Here you can see that these have been colored in one way, these have been colored in one way. So basically, these are the samples that we have from our training data. And these are of one class, these are of another class, these are of other class. There are 4 classes basically. And then we are trying to train a decision tree based on this data. So as you can see, so this is depth 1. What does depth 1 mean? As I told you earlier, that this is depth 1. The our first decision will lead us to depth 1, right? So when we have depth 1, we can only divide on just one decision, and this is the decision that it is taking, that okay, it is dividing the yellow from the others. With depth 2, it is being able to create another divide, say here, with 3 depths. Now with 3 depths, it is creating 2 divisions again. Here one is here, and another one is here, right? And with depth 4, it is creating so many more decisions. And basically, so what is this decision mean? This decision will be able to reach after say after it goes from there to here. This is one decision. So this is by this area. This is denoted by this area, right? And then another, this one perhaps it will be this one in this area. Okay, this is for different data, but I want to you to get the idea that we have some data, we have some classes, that is our terminal targets, that is the output, that whether it is of a particular class or not. And here we are visualizing how decision tree is forming divisions between the data. Say for example, when we were doing linear regression, for example, what we were trying to do, there was a graph, right? There was this a linear kind of graph, and then we're trying to make a model which will try to fit to this graph, and it will try to imitate this graph, right? Find out the equation of this graph. In a similar way, or if, for example, if had it been a linear classification example, right? So how it would work out? Say we have only this class and only this class. These two aren't there. So we can have a line which passes through the middle of these two classes, and then that line will be able to divide this data from this data, and that will be a classification kind of thing. So similarly, in decision trees, we'll be having only horizontal or only vertical lines. Why is that? Because it is dividing on the basis of one of the features. So say this is a feature and this is a feature. So first we're dividing on this feature. So if it is greater than this feature, some value of this feature, say for example, when we're having here 2.45 centimeters, so this is greater than 2.45 centimeters and this is less than 2.45 centimeters. And then when we were dividing, let's say here less than equal to 1.65, so this is again of petal, here it is petal width, so this is petal width, and here we're dividing these two data, right? And so on and so forth. So this is how we are going to visualize. This is another form of visualization of decision trees. Now, one of the best features of decision trees is that it allows us to visualize very easily. Another form of visualization that we can have, and that I'll show you, is called feature importance. So how does that work out? So let us see if feature importance we get. Yeah, so we have feature importances here. So let us just use this, right? And we are going to indices is equals to np dot arc sort. So basically arc sort means just sorting and finding out the first. Let us see what IMP returns. Then we will go on. Okay. Okay, I mean, we could have visualized here. We don't need to visualize because it's a very simple model, and decision tree will just return the importance of each of the features. Basically, what this is all about. So I'll just make it easier for you to understand this. Just a second. So we'll have features targets, right? I start target names. Oh, sorry, feature names. Sorry. Right. So basically, this addition tree will calculate a feature importance. Okay, and on the basis of that, it will tell us, which parameter is important for it, right? So here we have the sepal length, which is 0.00. So basically these two don't have any importance, and these two have the most importance, with the most importance being given to petal length and petal width lower importance, right? So the question now comes, how do we find out which one to divide on the basis of, say, on the basis of petal length or on the basis of petal width? How do we find out that? So that is where this Gini comes in. We also have entropy, so I'll be explaining in short how it works out, right? And from there you'll understand a basic idea of how feature importance is created. So let me just go to this, right? Okay. So let us say here we had division. So on the basis of, let me go to a new page. So first of all, we had something like just copy that data length. Okay. So greater than or less than equal to 2.45. Okay. Less than equal to 2.45. So this was one. This was one other one. Okay. Let us see. Right. Okay. Okay. So what is happening is that, say we just create this to just one till one depth, and we are having this two leaves. So what the, okay, I'm just doing it with binary data. Okay, first binary targets, it is only, let's say we have only versicolor and setosa in that way. Okay, uh, then I'll expand it to the other into multi-class classification class. So in, let us say, for example, let us go with the rainy example, because that will be easier to understand. Is it going to be raining today? Is it going to rain today or not? So let's say we divide it first on the basis of humidity. Now, how do we decide that this is going to be humidity or not? The value is easy to identify. That is it going to be less than 70 or is it going to be less than 80? That is very easy to understand. But is it going to be humidity or is it going to be something else? Right. So we had some samples. Let's say we have some 100 samples. Okay. Let's say 100 samples. Okay. And out of those, we know that already that let's say on 60 samples we have yes, and on 40 samples we have no, right? And then on dividing on these, then we are getting here, let's say 70 samples, and there we are getting 30 samples. So basically you have this data, and now after passing through this condition, we are going to have this kind of data, right? This is going to be 70, this is going to be 30, or perhaps 50-50, something like on those lines. And then let's say here we have, out of those 60 yes, we have, let's say 50 yes and 20 no. And here we'll be having the rest 20, so let's say 10 years, right? 10 years and 10 no, right? 10 years and 10 no. So this is already, we know these two information we already know from beforehand, and now we are predicting that, let's say the humidity is less than equal to 50. So we are dividing on this fact, and then we're getting this 70 and 30 samples, right? What we do here is that we'll calculate a function. Okay, let's say we use Gini. So we'll calculate the Gini purity, and it is calculated as, what is the correct prediction, right? So no, sorry, what will be the number of samples of this class here? So that is the 50 by 70 probability of this class being here. So what is this thing is 20 by 70, right? And here we are having again 10 by, oh sorry, I guess I made some mistake. Oh sorry, this is 20. Sorry. This is 10 by 30 and this is 20 by 30, right? Okay. Right. Now we are going to find out the this for this node, what is going to be a Gini factor. So basically, this is calculated as 50 by 70 square plus 20 by 70 square. Okay, and here we calculate it as 10 by 30 square and 20 by 30 square, right? So basically what we are predicting, what we are trying to calculate is that if this is 70, then how many of them are yes and how many of them are no? Here, how many of them are yes, how many of them are no? And then what we are, okay, let me just define the other function as well so that we can do both of them. The other function will be entropy. So entropy, how is that calculated? So when we go back to physics, we studied entropy. This has a very similar way of understanding. That is, here entropy. So say for example, what happens in entropy is that we know that say energy. So the energy will always be dissipated. It will be randomly distributed in the environment rather than being clumped up in a space, right? So energy. So from that concept, we are going to have a similar kind of idea here. We'll know where we are going to have that idea. Here entropy is actually, here we had some p square. Here we are going to have p log p. Okay. So then actually it will be minus p log p because p is always less than 1. So this will be a turn out to be a negative 1. So we are going to have a negative here, minus p log p, right? And that is going to be our entropy. And similarly, we can calculate for all these, all these yes and no for all the nodes, right? And so basically, what we end up doing is that we'll add again here. So this will be 50 by 70 log 50 by 70 plus dot, 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 dot. Whatever, you know what I am trying to do. And here also we are going to have that. Okay. And what we'll try is that, do here is that, or we'll calculate the same value here as well. So this will be 60 by 100 log 60 by 100 and then 40 by 100 plus log 40 by 100. Okay. I guess I did. Just a second. Just allow me to revise this one. I guess I committed an error somewhere. Just a second. Oh, okay. Okay. So yeah. So I am correct. So I was actually confusing it with the next step that I have to do. So basically, whether E, whether G. Okay. So next, what we are trying to do is so we find out. I'll just summarize a bit so that we have here. Yeah. So, we had some decision to make, and on the basis of that decision, we had some 100 samples, 60, 40, and here we found that there were 70, there were 30, 50, sorry, 60, 10, Okay, 60 10 or 50 20. Okay, 50 20. So 50 20, and here there were 10 20, right? And so we here we found out some E or say G. So I am now doing with E, and here we have E. Now what we do is that we'll combine these two. But how will we combine these two? So we did find out something, right? We found out that this is going to be minus P log P minus P1 log P1, P2 log P2. Okay, here also we have P1 log P1, P2 log P2. Now what we're going to do is that we are again going to do the similar kind of thing. So here we are having, so this whole value is for the 70, and this E value is for this 30. So we are going to add them again on this way on the proportion. So 70 by 100 into E, this is E1 and E2 plus 30 by 100 into E2. Okay. So when I'm doing this, I'm getting a total E value. Okay. And what will happen is that quite interestingly, when you calculate E here, as I pointed out at first, where 60 by 100 plus 40 by 100 and log all of that, this will always be less than this. Okay, you can check that out. You can go and check that out, and this will always be this value. As I say, this is E dashed. Okay, this E dashed is always less than this E. Okay, and whenever you subtract, basically what you'll find is, for example, this is 0.9 and then this is 0.7. Okay, so you'll have a 0.2, and this is what we call information gain. Okay, this will be information gain. Okay, basically what is happening is that here the, what I told you in what you had learned in physics, that we have some clumped energy, right, or further case matter, and it will just spread out, right? It will just spread out in space. In this case, think of it as having this spread out data, right? You don't know which one is of which class, right? It is spread out, and now you are trying to return to this state where it is clumped. In what sense? These two are separated, right? Say you have two sets of balls, right? By balls I mean balls with which you play, let's say cricket or anything else. Anyways, so these are red, these are blue balls, and then you just just randomly keep them in a in just one bag or one box, right? And after you transfer all of these, you will find out that they will be randomly distributed, and statistically the possibility of distributing all of these balls in this bag is like there's like trillions of ways. But if you want to have them in such a way that this is divided, then this is just one way, that here will be here there will be red and here is a blue, right? There's just one combination possible, and in the other case where you will find blue and red balls mixed up together, there can be infinitesimally many possible ways, which means that statistically this is having a entropy is always increasing. So this is having a randomized structure, right? So basically here also we use this randomized data, and here we are trying to decrease the entropy against the law of nature and making clumps of data. So basically this difference is our one step towards making these two different clumps of data. Okay, so that is the information gain. That is the information that we have gained to make these two clumps different, separate. Okay, so similarly we can do with Gini as well. it's easier to understand with entropy because you have the physics example with you. So that's the basic understanding behind how decision trees work. I hope I was able to explain to you all the stuff. Any questions till now before I move on? Any questions? Please answer. Okay. Okay, so let us try with another data set, this breast cancer data set. We can see that we have target 0 and 1 only. Is it malignant or benign given certain values, right? So we will try this one out. Okay, and the number of samples. How many samples do we have? Okay, it's 569. So let us see how this turns out. I'll just I'll not change the variable names. Without changing the variable names, it will work out obviously. So let us try how it works. Okay, so we have 0.093567. Okay, so this is a good one. This is a good one. Okay, let us try another error. Let's say we can have root mean square error as well. What are the error available? Okay, we can have log loss as well. No problem to score, but we don't have root mean square error. Okay, we can have mean squared error. Okay, let us try out mean square log error. Oh, sorry. Okay, 0.4. So basically, you won't actually understand if 0.044 is good or bad unless and until you try a number of models. Let us say we try with different kind of parameters. Okay, we'll come to parameters. I forgot to talk a bit about that. I'll talk a bit about that as well. So here we can go for the okay. So you see this here we have a better view. This is not a binary obviously because oh sorry. Sorry, this is a binary as well. Yeah, it's a binary as well. So basically here we are making only binary trees because obviously as I said, if we have three partitions to make, we can make two partitions and then again two partitions. So basically as you can see, we first have worst concave points, then worst area here, worst perimeter here, then we have symmetry area error and so on and so forth, and finally this is a very deep one, right? So we have 1 depth, 2 depth, 3 depth, 4 depth, 5 depth, and 6 depth. And let us see the important feature importance. Sorry. So you can see a lot of them turn out to be 0. Don't require them. Few turn out to be very small. So this one is very small. This one is quite small. This one is quite small. The major one is most important one seems to be this one, worst concave point. So you can see that there's a quite a similar relation to the Gini impurity that we have calculated. Okay, so that was Gini purity, right? This was Gini purity, and when we do 1 minus this will be Gini impurity. Okay, so here we have see, as you can see, we have worst concave points at the top. So basically, you can understand that the worst concave points will obviously the most important one, because had there been some other, there's a worst area, worst perimeter, then it's more important, then it would have been at the top. Because how are we calculating that? We're calculating using, say, Gini or using entropy as well. You can use entropy as well. I'll come to that, how we are going to do that. And basically, this will go on this way. Right? And it's very interesting, right? The value is 142.26. So it's dividing into 142 and 256. Okay. So as I was saying that we can do the parameters. So whenever you will be building some model, you will be all these dresses are very small, so they are having 500 rows. But when you will be going for some competition or say some real world data, you'll having say 5,000 rows, 5 lakh rows, 5 million rows, something like that, of that size, right? Of that, that will be very large. So in those cases, often just having just decision tree classifier and just object and with default parameters won't work. So in that case, what we will do is try to change these parameters and find out which one is the best working, right? So for example, we have criterion. Okay, so one thing that I'll mention here is that whatever the parameter changing that we need to do, we can do that using many ways. One of the ways is grid search. Okay, so we'll come to what grid search is and things of those sort later on, because we wanted to first tell you about the models or how they work, then we'll come to those all those details, right? So grid search is something that is often used to identify the best performing model. And all these are called hyperparameters. Why are there hyperparameters? Because these are parameters that can be changed, or that can be utilized to get a best performing model. And you need to, it requires human intervention. You yourself need to change that, or maybe you will write a program that will find out the best performing model by having tree recently classifier in this example, right? Okay, so here we can see that it's a criterion. So criterion is already always Gini or entropy, as I pointed out. Splitter is the best, or randomly, will it split randomly or will perform the best split? So best split, how will it perform? As I told in the case of entropy, it will find out the information gain. So the higher the information gain, the better it will be. So that is the maximum depth. Maximum depth of tree default is none, which means it can go on until it has been able to divide all the data into either yes or no, or in the case of multi-class classification, into all the classes, right? And then we have minimum sample split, the minimum number of samples required to split an internal node. Okay, so what is this one? If you come here, so as you can see here, the samples are, this is 254, so this is 5 plus 249, right? So as you can see here, this 27, yes, is only 6, so only 6, and it is dividing them into 2 and 4. So maybe this is not required at all, right? We can already say that this is malignant class. We don't need to require the other to be to divide into 4 and 2. Why don't we require that? Because when you go into so much depth, and at first we are having 398 samples, and then we go all the way till just 6 samples and dividing them. What happens is that there's some the term called overfitting. We'll again come to overfitting and underfitting in a later at a later session. But for now, just understand that overfitting means that it is memorizing the training data. But it is synonymous to what is meant by memorizing the training data. So basically, it is almost as if learning that if this comes, these values come, then this is this. If these values come, then it is malignant. If these values come, it's benign. But we don't want that. We want it to perform some mathematical calculations to understand what is going to be the class. Okay. So often that is why we restrict this minimum samples leaf. Okay. So let us try something. Let us try with entropy. We had entropy, right? Sorry, no, sorry. Criterion to be entropy. Let us try with max depth. We had something called max depth, right? And max depth will give only, let's say, 4. Okay. And minimum sample split. So mean sample split. Mean samples leaf mean how many samples you are required to get a leaf, right? So you can just find them out in the documentation. There are so many parameters. These are just a few. I mean, it seems that there are so many parameters, but when we go in the next session, we will study other models, you will see that there are so many parameters. You need to optimize not all, but some of them. So let's say in decision trees, we often optimize. We see the criterion is entropy, or Gini. We see the max state, minimum sample split, and things like this. So let us say that it has to have at least 20 samples to divide. So let us try that case and let us see. You see, the error seems to have decreased, if I'm not wrong. Let me do something. Okay. I'll just copy and paste this. So we'll be having both the values. So let me just print this at first, right? And without the parameters, right? Okay. Some error it seems. As both the values come out to be the same. Just a second. Okay. So as we can see, in this case it increases. In other cases it can decrease. So in this case we see that using these parameters is not good. So let us try with Gini once again, but with the other two remaining the same, and let us see how it turns out. Okay, so see, this time it decrease. So on a intuitive basis, you can understand that Gini performs better than entropy in this particular example. It doesn't have to be always. It can be entropy sometimes, it can be Gini sometimes, but seems that Gini in this case has better results than both that both the criterion being entropy and then also the default parameters. So when we restrict the depth to 4, here we had depth something like 7 or something, then it seems to perform better. So let us see how the graphs looks now, right? Let us try that. Uh, okay, see. So as we had specified that the depth will be at max 4. So as you see here, this is 4, right? And here you can see that just say this is class Benning. Already there is 28 and 5 are malignant, right? Here are samples 1 only. So even though it seems that this was better because this had so many more divisions, the thing is that this was dividing on the basis of on the training samples, right? And often in test cases that won't be the case. So you can say here as I was let me go to the okay, there's this code as well that you can use to get this kind of a graph. So as you can see here, these are the divisions that have been made, right? So the division tree could have just made a division for each of these, right? For each of these, it would have just made a division and said that, okay, this is what this is what this. That won't be a good one, right? You have to make some general decisions, not a particular decision that for this one, okay, we have these values. For this one, we have these values. No. So often the having a very deep tree isn't a very good idea. Okay. So as you can see, this is the way to go. Okay. So this is all about decision trees. One other topic that is there, and I won't go for any no. Okay. Won't go for any code as such, but I will say those in short so that in the next session we can begin without discussing all those details. We can directly jump into the models and stuff. So basically, you understood that there is this is a decision tree, but often with large data, what happens is that one decision tree is not good enough. It may not be able to get the best results, right? Say for example, you 30 people sit in a test, right? If individually each of them give the test and they predict, just let's say it's a MCQ based question, let's say JEE mains, right? And there are 30 people of different capabilities, different intelligence, although intelligence is same for everyone, but anyways, of different capabilities, and they sit and give the test, and obviously not all of them will have matching results, matching answers, right? But often you will find out that, let's say, the worst performing person may have had some correct answers which the best performing person or the best performing student wasn't able to get, right? It might happen, right? So here we can understand that always the best performing model doesn't have always the best answers. Maybe it also creates a few errors which might be pointed out by some other model, which might not be as good performing on a general basis as the other model, right? So this is just one example, right? So what if we could do something like this, that on the 30 students, instead of uh, asking them to give the test individually, what if we could combine the power of all the 30 students? Then that would be, then the results would be the best, as you can understand that more often than not, they will be able to predict the best answers. How will they predict? For example, let us say we average the results. Say for example, what does average mean? Okay, not average. I mean, we find out the which one is the maximum chosen. So that is how we find out, not exactly the average in the MCQ case actually. So we find out which one is in the voted the maximum, and that is how we'll choose one of the answers, and more often than not that will turn out to be true. So in case of ensemble learning, that is when we combine two or more models, can be similar type, it can be different type. Let's say one we have linear classifier and another we have decision tree classifier. One we have okay, I'll say the name, but we'll come to that later on in one of the sessions. That one we have SVC and another we have decision tree classifier, right? See, SVC is actually okay. We'll come to that later on. SVC is another model, another classifier. So basically, the idea is that, or maybe even there can be two decision tree models. One having a, say for example, Gini impurity as a criteria, and then having entropy as a criteria. You can have that as well. So basically, the idea is that we are combining two or more models. Now, how can we combine? We can combine in many different ways. Say, for example, we can combine using max voting, as I told you already. We can combine by averaging. We can combine by weighted average, right? So max voting is basically a classification. In a classification task, you will vote, all the models will vote for one of the target or one of the target values on the output. Say for example, you have true or false. Say out of three, two models have predicted true and one model has predicted false. So obviously it will be a true. The output will be true. Maybe it is wrong, but the output will be true. And that is how max voting works out. We can also have averaging. Say averaging is mostly for regression tasks. Say one has predicted 100, another predicted 120, another predicted 110. So it will average 110. So we are finding the average of three models. Then we can have weighted average. Weighted average is nothing but giving a weight to one of the models. Let's say we have a linear regressor and we have a decision tree regressor. And in terms of loss function, we know that decision tree regressor has worked better than your linear regressor. So in that case, we'll give more weight, say 0.8 weight or 80% weight to decision tree and 20% weight to linear regression. So that can be the way forward, right? So these are some basic ensembling techniques on ensemble learning that you will get, and then we can have some advanced concepts as well, and they work on a different idea, they work on a different way, and there have been some serious research in these areas. In weighted average or averaging, you don't have to get into all that kind of research, right? But overall, in ensemble learning, we have a lot of research, and obviously in stacking, in advanced ensemble techniques, that is stacking, blending, bagging, or boosting, we'll be having a lot of research as well. So what is stacking? Stacking is basically creating a stack. What is a stack? So one thing over the other. So basically we have models, let's say, and say there are we have three models. So we are stacking one model on top of the other. Basically it means that, let's say, you have a training set, and on a training set you train a model, and then on test set you find some as a prediction. Then you train another model on train set, and on test set you have some prediction. And in this way, you have some 3 or 5 or 7 or even number of models, anything. And what you do is that you have let's say you have 3 models, you have a 4th model, which will use these predictions from the from the other 3, and these predictions it will try to fit to the output data. Say for example, uh, there was say again the rainy, is it going to rain or no example. So let's say 2 models have predicted true and 1 model has predicted false. Then it might be the case that the other model, that the 3rd model is predicting correctly, it is false. So the model will actually learn this and try to have some kind of idea about when the model is when the models are predicting correctly, when the models are not predicting correctly. And in that way we are trying to firstly predicting on the train data using three or 2 or more models, and then using that prediction we are training another model which will be trained on the prediction of the previous models, and the output will be the whatever the test output is, which means that we know what will the test output. Obviously, if you don't know the test output, then we can't have that model. We can have that kind of idea. So in that case of, we can also have the validation data, say for example, and we are training on the validation data and finding out on a training data, on a testing data. So I hope you know what is train, test, and validation. Train means that in general, train means the data that is the model is training on. Validation means that that part of the data the model has not seen before, but we know the output, so we can evaluate the model and find out how it has been working. So for example, when I was calculating the error, the mean square error, for example, I already knew what was the output, what should be the output, and I have the predictions. So I can evaluate the model, right? And testing data in general, when you have train, validation, and test means that data on which you don't know the prediction. You don't know the ground truth, right? You don't know what should be the output, but you will have some prediction on the data. But when you have train and test only, in general, in that case, we by test we can mean that either we have the output, or either we have the ground truth, or either we don't have the ground truth. So it can mean both the cases. But anyways, returning to what I was saying, that on the train data set we are going to fit 2 or more models, and then on the predictions we are going to fit another model to the output. And also we can do another thing, is we can divide the train set into more components, and we will have one model that will be trained on one data set, on one part of the data set. Another model will train on the other part of the data set. In this way, we can actually have models which are trained on different parts of the data set. And this can be done only if the data set is large enough. Obviously, if you have just 500 samples and you want to do 3 models on 100 samples each, then that won't be a very meaningful one. But if you say 5 million, then you can, or 5 lakhs, then you can divide it into 3 or in 5 or 10 parts, and then train one model for each part, right? So that is overall what stacking is, right? Now we go to we'll go to blending. Okay, so basically, what is blending? So blending is actually a very similar example to stacking, but what we were doing is that there was that predicting on the training data. Here we are trying to predict on the validation data, learn on the validation data, and predict for the test as again. So what do I mean by training on the test data? In the second part, the model was actually looking at the train data, and okay, let me just draw so that we have a clear visual example of what I am trying to say. Right. Okay, or let me yeah. So, share. Right. Right. Say we had this data. This is a data. This is a test set, right? Now we were predicting say model 1, and the output is this. Model 2, the output is this, right? So and the ground truth. Okay, just a second. And the ground truth is here. This is the ground truth. So what we are doing, we are doing a third model, same dash, and we were, for example, getting this data and predicting what will the ground truth, right? The ground truth. So this is stacking. In blending, what we can do is okay. This is fine, right? We are having again some some data t and some m1 m2, but what we are trying to do is that we are dividing this, right, and training only on this part, not on this part. Okay, and we have these predictions, right, and we know the ground truth. Okay, but we are just using this portion to train the second model, right? Train the second model, and this is a bit. This is called blending. So this is a bit different from here. This one. So this one was that we had a training data, and we feed this and this, right? So M1 is fit on this and this, and predicting this. And in this case, M1 is predicting again this and this, but only this portion, and predicting on this portion, and the M dash model is actually predicting on this part only. So basically, this part hasn't been seen before by the model, whereas this has been seen before by the model. So there is a difference, and this is called blending. So that will be blending, and then we come to bagging. So what is bagging? Bagging, I told this idea before, but in that case we were using stacking, and here we are just going to just divide the data here as well, but we are not going to have a third model, because that is computationally very uh, you know we are very limited, so that will be having a very computational effect on us. So that is why we are going to have some data, and we are going to divide them into portions, and then we are going to use m1 sorry, the models m1, m2, and m3 and m4, and then getting the output. This is the ground, this is the prediction values, right? And then combining them in some way. You can use max voting, you can do averaging, so anyway, and here we'll have the prediction. So this will be something like this, and so basically here we have models, but they are independent of each other. Maybe the same models, maybe this is a decision tree, this is a decision tree, the others as well we can have decision trees, but here particularly it is more often than not that we have a same model, but maybe decision tree, maybe some other model, that but it is maybe having a different parameter, or it is having a different data set. So in this case we are having different data sets in bagging, right? And finally we go for boosting. Boosting is a bit of a complicated, not very much complicated, a bit complicated to understand. So basically in boosting, what we'll do is that we will have the data, and we will train one model, say a decision tree for example, and we are going to train the data, and So we'll be having, say, this is entry classifier and true or false, true and false. And so it has divided that this portion is true. Let's say this portion is false and this portion is true, right? But what happens is that here we are having many negative samples which are actually false. So, but we are also having some true data, and here we are having some true data, but again we have some false data, right? And maybe something like this occurs, right? So these two are errors and these here are errors, right? So these are errors here. So basically what boosting does is that in boosting, special weightage, there will be a second model. Obviously, in ensembling we have two or more models. So there is a second model that in which special weightage will be given to these samples in which there has been some error. So you understand it. You understand the intuitive idea that basically we are trying to predict better on those data on which we are having some error, and this cycle will go on. So for example, here from here we are going to have, let's say, something like false, and this will be true, and we are having a normal examples, but here we have one positive, and again here we are going to have, let's say, two or three positive from negatives from a lot of positives, right? So basically that is the idea, that by training a model with special weightage on these particular samples, then we are able to reduce the model error, right? And I guess so, yeah. So boosting, this is boosting, and particularly boosting has seen a lot of outcomes, because averaging and max coding can be done by anyone. Although in sklearn we have some classes, but boosting, you will see there's this ada boost. There will be ada boost means adaptive boosting. We'll see there's light GBM. Light GBM is a later one. First, actually, after this we already had something like called gradient boosting, right? Gradient boosting. Then we had XG boost, and then we had light GBM, and then we also had something called cat boost. So maybe we won't be covering all of these models, but I'm telling the names so that you go and search all of this and learn how they are being used. Obviously, you need to learn on some data set. Do not use a erased data set because it's very small. If you get a larger data set, you'll obviously get one. Go to Kaggle, go somewhere, and you will get some data, and try all these models, and you will know, right? So
আচ্ছা
I
দাদা,
guess.
মুভি রেকমেন্ডেশন সিস্টেমে কি মানে ইউজ করা হয়, মানে কোনটা? সেন সেন দেখছিলাম একটা ক্যাগলে এক্সজি বুস্ট ইউজ করেছিল ওখানে, আবার আরেকটা ইউজ করেছে।
Okay. So মুভি রেকমেন্ডেশন সিস্টেম বেসিক্যালি বলতে গেলে যদি আমরা ইয়েতে ভাবি, সত্যি করে মানে রিয়েলিস্টিক মানে রিয়েল এক্সাম্পলস কি ইউজ হয় সেটা আমি বলতে পারবো না, বিকজ দেখতে হবে। বাট যদি মডেলস হিসাবে দেখিস দেন তুই যে কোনো
হ্যাঁ,
মডেল ইউজ করতে পারিস,
মডেলই
ঠিক আছে?
বলছি।
হ্যাঁ, তুই যে কোনো মডেল ইউজ করতে পারিস, সেটা ডিপেন্ড হয়ে তোদের ডেটাটা কি আছে তার উপরে তুই কতটা ভালো ফিট করতে পারছিস। মানে বেসিক্যালি ফিট বলতে আমি কিন্তু ভ্যালিডেশনের উপরে বলছি, কিন্তু মানে ট্রেনিং এটা তো ফিট যে কেউ ভালো করতে পারে, কিন্তু ভ্যালিডেশনের উপরে তুই কতটা ভালো করতে পারছিস সেইটা দেখতে হবে। এটাতে মানে কোনো পার্টিকুলার মডেল নেই। আমি যেরকম আগে বলেছি, মডেলটা তো আর 1 মাস পরে তোরা এতগুলো মডেল শিখে যাবি যে দ্য মডেল ওন্ট বি much of a important. It won't be important. The important will be the theory behind all these models and how they're working, because you will always need to optimize any model that you are trying to find. তো মোস্টলি ডিসিশন ট্রি বা বুস্টিং রিলেটেড মডেলসই থাকবে, বিকজ মেশিন লার্নিং মানে উইথাউট ডিপ লার্নিং, মেশিন লার্নিং বা ইভেন অফেন ডিপ লার্নিং কে ইনক্লুড করলেও অনেক সময় মেশিন লার্নিং এর মধ্যে ডিপ এই ট্রি বেসড মডেলস, বুস্টিং কি এটা ট্রি বেসড মডেল ইউজ হয়, তো ট্রি বেসড মডেল গুলো বেস্ট পারফর্ম করে।
You can also
So-
use XGBoost can also be used for boosting movie recommendation systems.
হ্যাঁ, তো তুই সেটাই বলছিস, তুই এক্সজিবুস্ট ইউজ কর, লাইট জিবিএম ইউজ কর, তুই
Anything.
ক্যাট বুস্ট ইউজ কর, যেটা ইউজ কর, তোর দেখতে হবে তোর বেস্ট পারফর্মিং মডেল কোনটা হচ্ছে। এই বেস্ট পারফর্মিং মডেলটা কি বার করবি এই জিনিসটা আমি এখনো বলিনি, এটাও আমরা প্ল্যান করে রেখেছি, নেক্সট 4 to 5 সেশনস আমরা প্ল্যান করে রেখেছি। তো চাপ নিস না, সবই আফটার 4 সেশনস ইউ উইল নো হোয়াট টু ডু এন্ড হোয়াট টু সার্চ এন্ড হোয়াট টু আন্ডারস্ট্যান্ড, মেক আউট অফ অল দ্য ডেটা। তো একটু আমাদের সাথে বিয়ার করে যা। স্যার আমরা রেকর্ডিংটা স্টপ করতে হবে এখন।